Hello everyone, welcome to the 18th video lecture of class 9 science. So we are dealing with a third unit, that is electric charge and electric current. So in this video lecture we will be learning about electromotive force, potential difference, resistance. So just to recall the previous video lectures, we have till now learnt about electric field, electric force, electric potential, electric current and direction of current. So first we studied the electric force concept, where we learned there are two types of charges and one is positive and another one is negative. Whenever we bring two charges nearby, so they experience either a repulsion or an attraction. So this repulsion or an attraction are nothing but the forces. Okay, so if we bring two like charges, they will repel each other, and if we bring two unlike charges, they will attract each other. So that was about the electric force. Then we studied about electric field, where we stated that electric field is an area or a region where we can feel the effect of an electric charge. Okay, whenever we bring a unit positive charge near to any charge q present over there, the how much effect is felt by this unit, how much force is felt by this unit charge in that place is called as electric field. Okay, then we learned a concept regarding electric potential. So what is this electric potential? So whenever we talk, we just said that we have to bring a unit positive charge from nowhere, right? So when bringing a unit positive charge from one place to another place, or moving from one place to another place, we need to do some work. Okay, so that work is nothing but the electric potential. So the work done in bringing a unit positive charge from infinity to a point is called as the electric potential of at that point. Okay, if I am bringing 1 coulomb of charge from infinity to point P, the work done in bringing the 1 coulomb of charge from infinity to point P will be the electric potential at point P, not at any other place. It will be the electric potential at point P. If I am bringing a unit positive charge from infinity to a point Q, then that work done will be the electric potential at point Q, not at P. Okay, so it is specific regarding the places. Okay, then we studied about electric current. So till now we discussed about the charges when they were stationary, that means when they were not moving. So what happens once they start moving? Then the concept of electric current comes into picture. So this electric current is nothing but rate of flow of charges, or the amount of charge flowing per unit time, or in 1 second. How much charge is moving in unit second, or in unit time, or in 1 second is called as the electric current. Therefore we write I is equal to Q by T, where Q is the charge, T is the total time, and I is the electric current. And we even studied the unit of electric current is ampere, and the instrument used to measure the electric current is ammeter, and we always connect the ammeter in series to measure the current in the circuit. Okay, then comes the concept of direction of current. Okay, so it was by convention we say that the current direction is the opposite of the direction of movement of electrons. So if the electrons are moving from right to left, the current will be in the direction of left to right. That is by convention, and we discussed this concept of reversing these things, all those things in the previous lecture, and it is given clearly in your textbook too. Okay, so these are about the things which we learned in our previous classes, just an introduction and a recap. Okay, so moving on, the first concept which we will be learning in this class is electromotive force, right? So the name itself says it is a kind of a force. Okay, so for this, just imagine a pipe, water pipe. Okay, so this is a water pipe, and I am joining, the two ends are joined at this point P. Okay, so now we are filling the water inside and then joining at this point P. So since we have kept it inside, so it is filled with water. So will there any be movement of this water? Will it be circulating in this pipe or it will be stationary? Obviously, it will be stationary, right? So without, doing anything, we cannot move the water inside this. Yes or no? The same thing. Okay, if we want to make this water to move inside this pipe, what we actually need to do is nothing but we can insert a water wheel in between the flow and make it to rotate and further use that rotation to, one second, yeah, yeah, what happens if we insert a pump or a water wheel like given in the picture, then what happens, that wheel will move, so the water will also start to circulate within that water pipe, right? So what exactly we have done here is, suppose you insert a pump in between this pipe. The pump pushes the water, then the water will start moving in the tube. Now the moving water can be used to produce some work, right? So we can insert a water wheel in between the flow and make it to rotate and further use that rotation to operate the machinery. You're understanding the concept, right? So why we actually need to rotate the water over there? So that turning water or the circulating water will help us to operate the some other machinery. Okay, so here the concept is we need something over there to just to circulate the water filled inside the pipe, right? So what actually this pipe is doing, pump is doing, nothing but it is applying some force to move the water in some particular direction, right? So similarly, if you take any copper wire, circular copper wire, it will be full of free electrons. Okay. Now, however, they will not be moving in a particular direction. You need some force to push the electrons to move in a direction. So current, when we are studying, it will be moving if the electrons and the charges are moving in one particular direction, and that flow will be called as electric current, right? So to generate, when we talk about the electric current, the electrons or any charged particles should move in one particular direction, not randomly, right? So to make this electrons to move in one particular direction, before they were stationary or they were randomly moving, so now we want to make them move in one particular direction, as we made the water to move in one particular direction using the pump. Here in this case, what we exactly do is we keep a battery or a cell. So what it does, like the pipe, like the pump in the above system, water system, in the electric network, battery will make these electrons or the charged particles to move in one particular direction. Nothing but it will apply some force, kind of a force, okay, to make these electrons or the charged particles to move in one particular direction. The force which is offered by this is nothing but the electromotive force. As the pump does in the case of water system, the cells or the batteries will do the same thing in the electric network. Devices like electric cells and other electrical energy sources acts like pump, pushing the charges to flow through a wire or a conductor. The pumping action of the electrical energy source is made possible by the electromotive force. I hope you understood. Okay, the pump in the case of water system is nothing but similar to that of the batteries in or the cells in the electric network. Okay, they just try to help in pushing the electrons or the charged particles in the electric network. So the electromotive force is represented as, it's called as epsilon. Okay, it is not E, it is epsilon. Its pronunciation is epsilon. Okay, it is represented by this letter. Okay. So this electromotive force will be written as EMF, electromotive force. Okay. The electromotive force of an electrical energy source is the work, excuse me. The electromotive force of an electrical energy source. Electrical energy. The EMF of an electrical energy source. The electrical energy source is nothing but your battery, your cell. They are nothing but the electrical energy sources. Okay. The EMF of the battery or the any other electrical energy source is the work done by the source in driving a unit charge around the complete circuit. So, what actually it does, like the pump helps in moving or rotating the water, right? So here the EMF of the electrical energy source or the battery will help in moving the electrons or the charged particles, right? So how much work is done by these sources in moving these electrons or the charged particles? The unit charged 1 coulomb of charge. So how much work is done by this battery in moving 1 coulomb of charge in that complete circuit? That is, so this is our circuit where it is connected with the battery. Okay, so how much uh, work is done by this whole battery in moving 1 unit means 1 coulomb of charge in one complete circuit. Okay, how much work is done by this battery is called as EMF of this battery or the cell. Not the battery, it is a cell, right? The battery is nothing but combination of more than one cells, right? Okay. So it can be calculated as EMF is equal to work done by Q, W by Q, where W is the work done and the SI unit and Q is the charge. The SI unit of EMF is joules per coulomb, because SI unit of work done is joule. So joule per coulomb will give you the value of EMF, or joule per coulomb is also written as volt. Okay, how much volt? The EMF of an electrical energy source is 1 volt if 1 joule of work is done by the source to drive 1 coulomb of charge completely around the circuit. We say that there is the EMF of the battery is 1 volt. When we say that, when 1 joule of work is done in moving 1 coulomb of charge around that in that complete circuit. Okay, if we need two joules of work to move 1 coulomb of charge, okay, 2 joules of 2 joules of work to move 1 coulomb of 1 coulomb of charge in the complete circuit. Okay, so how much will be the volt or the EMF of this battery or this cell? It is nothing but 2 joules divided by 1 coulomb, which is nothing but 2 volt. Okay, if through 3 joules is used by 1 coulomb of charge, then it will be 3 volts. If 2 joules of work is, 2 joules of work is done to move 2 coulomb of charges, then how much will be the EMF? 2 divided by 2, it will be 1 volt. Okay, I hope you are understanding. Okay, then now let us see one small problem based on the concept of EMF. The EMF of a cell is 1.5 volt. Okay, you are given with the value of EMF. What is the energy provided by the cell to drive 0.5 coulomb of charge around the circuit? Energy is nothing but the work done. Okay, it is nothing but the work done. So now you are given with EMF, you are given with charge, you have to calculate the energy, nothing but work done. Okay, so how to calculate? One simple equation, epsilon EMF is equal to W by Q. We know the value of EMF, we know the value of charge. So W, if we want to calculate it, the equation will be W is equal to epsilon or the EMF into Q, where EMF is 1.5 and Q is 0.5. So it will be 0.75 joules. Okay, one small equation, that's it. I hope you're following. Then moving on. So whenever we connect or do a circuit, we will not connect the one terminal of the battery to the another terminal, right? Never we do this. Like, this is a cell, positive and negatives are there. If we are connecting this, we won't do this, right? We will either connect something in between. Let it be our bulb, right? Bulb will be connected, or any other appliances will be connected, fan will be connected, your DC motors or any kind of motors or any appliances will be connected, right? Okay, so we won't connect one terminal of the cell to the another terminal. Okay, so this is how a certain amount of, so what actually it does when we connect the bulb over here, what actually it does? So when we are, it is a closed path now, and we are giving one positive, one negative terminal to one side and the other side of this bulb. What actually it does? So due to the presence of this battery, the charges will get pumped up. Yes or no? They start to move, right? When they start to move from one point to another, like one terminal to another, so what happens? So they will start to move, the electrons move from negative to positive. Okay, let them move. So when they start to move, the electric current will be present. So this electric current will be used by, electrical current is nothing but the electrical energy which will be provided by this cell, will be used by this bulb, and this bulb will take that electrical energy which is given by this cell to get converted into the form of light. If you connect it into a coil, it will become heat, right? There the electrical energy is getting converted into the heat energy. So it will be going into, in the case of fan, it will be getting converted into mechanical energy. So this is how the electrical energy is used in a circuit to get converted into different forms. Okay. So that's what we connect a bulb or a small fan or any other electrical devices in a circuit and use the electric current to drive them. Okay, this is how a certain amount of electrical energy provided by the cell or any other source of electric energy is converted into another form of energy like light, heat, and mechanical, or so on. So for each coulomb of charge passing through the light bulb, or any other appliances, the amount of electrical energy converted to other form of energy depends on the potential difference across the electrical device or any component. Okay, so for example, so here is one battery, and here is my, I mean, I'm keeping a bulb. Okay, so what happens? So now I'm keeping a 2 volt battery. What happens? The bulb may glow, may not glow. So what I do, I'll take this and I will make it as 4 volt battery. So now the bulb will glow. Yes or no? The bulb will glow obviously. Now I'll take it off and keep a 5 volt battery. Then the bulb will glow with more brightness. Yes or no? It will glow with more brightness. Yes. If I further increase, the brightness will increase. And if I further increase more and more, what happens? The bulb will burst out. So why it happens? Okay, so why actually it happens is, whenever I connect any appliance or any electrical appliance to a battery or the cell here, and at this point and these points, like point A and point B, will be having a difference of potential. Two different points will have two different potentials. Okay, so this difference in potential will go on increasing when you increase the battery. Okay, when you increase the EMF, I mean more EMF batteries when you keep, then the more potential difference will be created across the terminals of this electrical appliance. So more the potential difference, more will be the brightness. So at one point of time it will reach its saturation level and bulb may burst out. Okay, so that is what they are saying. For each coulomb of charge passing through the light bulb, the amount of electrical energy converted into other form of energy, here it is light, depends on the potential difference across the electrical device or any electrical component. The potential difference is represented by the letter capital V. Okay. So V is also calculated as W divided by Q. Now again, what is this W? Work done in moving 1 coulomb of charge, right? Where W is the work done, the amount of electrical energy converted into other forms of energy measured in terms of joules. Okay, so here you can clearly see there is a difference in the definition. The first case, when we define EMF, there we define as the amount of work done in moving 1 coulomb of charge in the complete circuit, right? Here it is the work done or the amount of electrical energy converted into the other form of energy. So there is a bulb given to you, right? How much electrical energy is converted to other form? Okay, per unit charge, that is the volt, I mean potential difference. The SI unit for both EMF and the potential difference is the same, that is V volt. Okay, so note the difference between EMF and the potential. In simple words, EMF is the value of the potential, EMF referred to that voltage developed across the two terminals of an electric source when it does not produce any current. Just simple as that. Okay, you have a battery or a torch, right? Where we use cells. So the EMF refers to the value of the potential when the torch is off, when you are not taking any current from it. Okay, the cell as it is. Now if you connect that cell, or when you switch on the torch, what happens? The torch is, the light is coming from the torch. From where it is coming? The electrical energy which is stored in the cells are getting converted into the light energy. That means you are taking the current or the electrical energy from the battery to produce the light, right? Now what will be the potential difference across the terminals of these battery will be called as the potential difference. Like when you are not drawing any current, that is called as EMF. For the same battery, when you draw a current, there will be a drop of potential, and that potential is called as potential difference. See, this is a battery. One is positive side and the another one is negative side. Okay, this is a cell. Now, see, here it is a positive side and this is a negative side. That means there is a difference between the two terminals. So this difference will be called as EMF. Now I connect this to a bulb. Okay, bulb. Now the bulb is glowing. Okay, still there is a difference at these two. This is a positive potential terminal, this is a negative potential terminal. Now this potential difference created here will be called as PD, that is potential difference. When you are not drawing any current, then it will be called as EMF. When you are drawing any current from that cell or a battery or any electrical energy source, then you call it as potential difference. To measure the potential difference across the component in a circuit, the voltmeter must be connected in parallel. So to measure current, we use ammeter, and to measure potential difference, we use voltmeter. And the ammeters are connected in series, and the voltmeter is connected in parallel. So you can, the positive red terminal of the voltmeter is connected to the positive side of the circuit, and the negative black terminal is connected to the negative side of the circuit, as shown like this. Okay. So this is how the actual setup will be, and this is how we symbolically show it. Okay, the red, this is a battery, this is a bulb, and this is the voltmeter. Sorry. So all positives are connected to positive, right? And all negatives are connected to negative. This is nothing but the parallel setup. Okay. So let us do a simple problem. A charge of 2 into 10 to the power 4 coulomb flows through an electric heater. So this much of charge is passing through an electric heater. The amount of electrical energy converted into thermal energy is 5 megajoules. Okay, M here is mega. Mega is 10 to the power 6. Kilo is 10 to the power 3. Right? Mega is 10 to the power 6. Giga is 10 to the power 9. Okay. Compute the potential difference across the ends of the heater. So it's also a small equation. V is equal to W by Q, where W is 5 into 10 to the power 6 joules divided by 2 into 10 to the power 4 coulombs. Okay. So it will give you the value of 250 volts. A simple small problem. Yes? Okay. So this is about potential difference and the EMF. So what is the difference? You have understood the same concept. Only difference is the EMF when you are not drawing the current from the cell or any electrical energy source. So when you are drawing the current, drawing in the sense taking the current, okay, from that taking the current, in the sense taking the electrical energy, using that electrical energy from that cell or the battery, then we call it as potential difference. Okay, so the one more concept which we'll be learning in this video is resistance. Okay, the resistance is nothing but whenever these electrons or any charged particles are moving in a conductor or any wire, so they are not freely allowed to move. Like this is a conductor, okay, I have so many electrons, they are moving in one particular direction. These electrons are not freely allowed to move. Okay, so what happens, this material will have a property due to which it will resist the flow of these charges. Nothing but, maybe it is a positive, you can think. So any, the flow of charges are nothing but the current. Okay, so by the, due to the such property of an material, what happens, there will be a resistance or there will be an opposition. Like you study, whenever we move, there is a friction which is opposing the movement. Similarly, in the case of electricity or electric charges, electric things, electrostatics, we have a kind of a resistance offered by the property of that material. It is due to the material nature. Okay, so it opposes the flow of the current. So in one direction, if this is the conductor or any wire, so this is how the in this is the direction of current, electric current. Okay, then there will be an opposition, and that opposition is called as resistance. The resistance is the measure of opposition offered by the component to the flow of electric current through it. For example, I am taking copper wire. How much resistance or how much opposition the copper is providing for the flow of current in it. Different electrical components offer different electrical resistance. So the different or different materials and the different things offer different amount of resistance. Conductors and insulators are based depending upon the resistance. So when you are having high resistance, so what happens, the flow of current will be very negligible or almost zero. So such materials or the such things are nothing but your insulators. Okay, so if you have such things which will easily allow the electric current to pass through, that means there the resistance is very low, they are called as conductors. Okay, the SI unit of resistance is ohm and its symbol is like this, it's called as omega. The symbol is called as omega. Okay, the ohm is the 1 ohm is the resistance of a component when the potential difference of 1 volt applied across the component drivers a current of 1 ampere flows through it. So one, how actually we define 1 ohm is when 1 volt of potential difference is applied across the terminals of a conductor, if it could produce 1 ampere of current, then we say that that object has got, or that component has got 1 ohm of resistance. Okay, we can also control the amount of flow of current in a circuit with the help of resistance. So resistance, what it does, it will oppose, right? If it opposes less, the flow of current will be easy. If it opposes more, the flow of current will be very less. So depending upon this, we can actually control the flow of electric charges or flow of current in the circuit. Such components used for providing resistance. So the materials or the things which are used to provide the resistance in the electric circuits are called as resistors. These resistors can be fixed or variable. So there are resistors whose values you can change, and there are resistors whose values you cannot change. So the fixed resistors are also available, and variable resistors also available. So that's it for the day. Thank you.